Alrighty, today we are going to finish Chapter 6 finally. We're going to finish up with graphing radical functions, because we've done everything else with radicals. We've added, subtracted, inverted, multiplied, divided. We've done everything except for graph. We've solved even equations. That's what we finished up yesterday. So now we're going to be graphing radical functions. This box is showing us the parent square root function, y equals square root of x, section 6.4. This shows us y equals square root of x. Now, we've been talking about square roots since the beginning of the year because I've been talking about domains since the beginning of the year. We have mentioned several times that you cannot take the square root of a negative number. But you can start taking square roots at 0 and go bigger. That is why your domain is 0 to infinity. Or you could also say, because look at this graph, it exists everywhere from 0 and to the right. So the domain of this graph is 0 to infinity. The square root of 0 is 0, and the square root of every positive number will be a positive number. That is why the range is 0 to infinity as well. Or you could just look at the graph and see that it exists at every y value from 0 up. There you go. Now, square roots are the inverse of quadratics, and their graphs are parabolas. So if you turn it sideways, you'll see you have half of a parabola. If I had the other half of this parabola, I could call this a vertex. But since sideways parabolas are no longer standard in the state of Florida for you to learn in Algebra 2, we don't have a sideways parabola, I can't call that a vertex. But it is an endpoint. So this graph does have a beginning point, and the parent function's end point is at 0, 0. This is not an interval, this is the coordinate, 0, 0. Square roots are functions, and all functions behave the same way using rules of transformations. So this would shift you left and right away from 0, 0. This would shift you up and down away from 0, 0. You find the endpoint of a square root graph the same way you would have found the endpoint of a quadratic. What makes the inside equal 0, comma, the number to the far right, h, k. So we've been practicing that all year. What makes the inside equal 0, comma, the number to the far right. It's exactly the same way for absolute value graphs as well. All right. So it's important that you know that this graph is supposed to go up and to the right. That's what it should do. Of course, transformations could switch some things around and move some things around. Specifically, the number on the front, this number could turn the graph upside down. So just like quadratics, if the front number is positive, the graph points up. And if the front number is negative, the graph points down. Let's go ahead and write that in here. Let's see. If a greater than 0, graph up. It's supposed to go up. So as long as you haven't turned it upside down with a negative on the front, it's still going to go up. Of course, if that front number is negative, then the graph will go down instead of up. The graph is supposed to go to the right, where the positive x's are. So as long as you don't put a negative number in the front of this x, it will go towards the positive x's on the right. So if you see a plus sign or x itself is just positive, then you go to the right. But if you reflect over the y-axis, that means switch the sign on the x. Yep, so if you see a minus x, your graph is going to go to the left. One of the most important things you could do with a graph before you find any coordinates is decide what it looks like based on transformations. If you can do that, you'll probably whittle down multiple choice graphing questions down to 2 options, and then it's 50-50. And that's just based on transformations. Transformations are important. They're never going away. Cool. Let's get some practice in. There's a positive number on the front of this radical. So which way does that tell me my graph points? Up. There's a negative number in front of this x. Which way does that tell me my graph points? Left. So this is up, because vertical, outside. So outside stuff affects the up-down. Inside stuff affects the left-right. So this is up and to the left. We know our graph is going to look something like this. Like a shooting star. All square root graphs look like shooting stars, essentially. It's going to go up and to the left like that. That end point is essentially free money. Yeah. What makes the inside equal 0? What makes the inside equal 0? 4, comma, the number to the far right. I know my endpoint is at 4, comma, negative 3. So I've been telling you all year, what makes the inside equal 0. And I've told you several times it's because of transformations. But I can give you another reason now, specific to these, why we want to look for what makes the inside equal 0. And that is, you're going to have to be able to graph these things on a no calculator test. And it says square root. So real quick, what's the square root of 3? No, that's 9 squared. That's the square root of 3. Ooh, you see how you don't know? That it's because it's not pretty. It's irrational. That means we can't just, substitute any x value we want into this thing. And if I put an x equals 1 right here, it says square root 3. And I don't know what 2 root 3 minus 3 equals for a y value. So we actually need to be a little bit more intelligent about what x values we're going to plug in. What kind of numbers do we want to see occur underneath our square root bar? Nolan? A perfect square. Perfect squares. We need what's underneath the bar to be a perfect square. Not plug in perfect squares. No, no, no. We need whatever's inside here to be equal to perfect squares. So what is the absolute smallest perfect square that we can talk about?
4, 1, 0.
0. 0 is the smallest perfect square. It's 0 times 0. After 0, what's the next smallest perfect square? 1. 1 times 1 is 1. And after 1, what's the next smallest perfect square? 4. 2 times 2 is 4. So here's what's going on. Every single time you go to graph a square root function, you are going to try to figure out what makes the inside equal these 3 values, 0, 1, and 4. Why those 3? Because I'm requiring you to plot 3 dots for a square root graph. And this is what you want to occur underneath the square root bar, so that way you don't have to worry about graphing a nasty, irrational decimal. We're trying to figure out what makes the inside equal that. Yeah, because these are the first 3 perfect squares. And we could take the square root of those, can't we? So we go, what makes the inside equal 0? What makes the inside equal 1? And what makes the inside equal 4? By the way, I'm just saying the inside. I could have said the academic vocabulary of radicand, or I could have just said the argument of the square root function. Regardless, I'm just going to keep saying inside, but just know that the inside of a radical is called the radicand. There's a D on the end of it. Or you could say it's the argument of the function. It's up to you. Anyway, let us solve for these 3 things. 4 minus some number is 0. We already know that number is 4. See? 4 minus some number gives us 1. What would I have to take away from 4 to get 1? 3. And 4 minus something is 4. These are the 3 x values that we are going to concern ourselves with. We are going to build a t-chart. And we put these 3 x's on there. 4, 3, and 0. You already know what the y value is, though, when x is 4. It's right there. It's negative 3. I mean, look, 4 minus 4 is 0. Square root of 0 is 0. 0 times 2 is 0. 0 minus 3 is negative 3. Yeah, now you're just plugging them in. Let's get our other two y values. Let's take x equals 3, and let's plug it in. 4 minus 3 is, you guys can shout it out. 4 minus 3 is 1. Square root of that is 1 times 2 is 2, and 2 minus 3 is, there we go, negative 1. And then you plug in 0. So 4 minus 0 is, whoa, whoa, whoa. Okay, one more time. 4 minus 0 is 4. Square root of that is 2. 2 times 2 is 4, and 4 minus 3 is, how about that? Great. Let's put these 3 coordinates on our picture and connect our dots.
What is 4 negative 3? Is that the...
That is the end point for negative 3. In fact, I'm going to go ahead and write EP next to it for end point. Then I have 3, negative 1, and I have 0, comma 1. With those 3 coordinates, you will not be able to accidentally draw a straight line, and you will not be able to accidentally draw a parabola, especially if you wrote EP, and you'll know which way the arrow has to go because you're not going to go to the end point. You're going to weave from the end point. So I'm just going to connect my dots with a nice blue curve. Yes, Hunter? Never mind, he says. All right, I must have answered it.
No,
He just figured it out. Okay, whatever. There it is. How we found these three x values, you mean?
subtraction.
No, are you asking where these 3 came from? No, okay, so these are perfect squares. These are the 3 smallest perfect squares. So we're going to figure out what gets us a 0 under the square root bar, because the square root of that is 0. What gets us a 1 underneath the square root bar, because the square root of that is 1. What gets us a 4 under the square root bar, because the square root of that is 2. So these are the first 3 perfect squares. And they will always be the first 3 perfect squares, which means anytime it's a square root graph, you will always figure out what makes this occur. Okay? Yes?
So you found the 4, negative 3 first, right?
I did, yeah. I found 4, negative 3 first just because it's what makes the inside equal 0.
Yeah, do we always find that first, or can we just do that?
Well, you need to always figure out what makes the inside equal 0 because that's the smallest perfect square. And that will always end up being your end point. Always. Any other questions about it? No? Okay. Hey, did you notice on the homework the space that I gave you between the equation and the grid? You see that space? That's where you're going to put this work. This is what I want to see. If all you do is draw the graph that I put on my answer key, I'm just going to give you a 0 for it because it looks like you copied my homework, yes?
Okay, so I have a question.
You have a question, I have an answer.
So to do this, like for instance, y and then x equals 4, we do 4.
Why, right here?
Yeah.
What I did was
No, not that. Like to get the y.
to get the y value, I plugged the x value into the function.
Oh, okay. Got it.
Yeah, anytime you have an x and you want a y, you just plug it in. Next. All right. So the first thing that you're going to want to do is you're going to want to decide. Whoa, my computer just did something weird. Hold on. What's going on over here? Let me pause the video while I try to. All right, figured out. Computer's fixed. So what we're going to do first is we are going to decide which 2 directions this thing points. I see a minus sign right here. Which way does that make it point? Down. Outside is vertical stuff. Vertical outside. So this makes it point down. Which way does this make it point? Left. I have it down and to the left. Down and to the left, just like that.
What do you do with that information? Like, what does that
You know exactly what the graph looks like.
Well, once you know once you graph it?
Only if you graph it right. What if you did your math wrong and then your points don't match up with the way you know it should look? Then you know to go back and check your math because your knowledge of transformation tells you what it has to look like. All right. Because it's easy to see, what makes the inside equal 0?
Why is 6 in front of x?
Because it is. What makes the inside equal 0?
6.
6. And if you plug 6 in, you'll get the y value of 1. Great. So, once again, we're always going to figure out what makes our inside equal the first 3 perfect squares, and we already know what makes the inside equal 0. It's right there, but I'm just going to write it out. What makes the inside equal 0? What makes the inside equal 1? What makes the inside equal 4? We already know that 6 minus 6 is 0, so I know the first x is 6. What would I have to take away from 6 to get a 1? 5. Cinco de Mayo. And what would I have to take away from 6 to get a 4? 2. These are our 3 x values that we will plug in to get our y values. Here is my t-chart with my 3 x values on it. And by the way, you already know what y is when x is 6. It's 1. Let's find out. So I'm not sure. So let's take this 5 and let's plug it in. 6 minus 5 is 1. The square root of that 1 is 1. Make it negative. Negative 1. Negative 1 plus 1 is 0. Then, take x equals 2 and plug it in. 6 minus 2 is 4. It had better have been. Look, we forced that to happen. Anyway, 6 minus 2 is 4. Square root of 4 is 2, but make it negative. Negative 2. Negative 2 plus 1 is negative 1. Those are your 3 coordinates. 6, 1 is your end point. So I'm going to put a little EP there so I know not to draw my arrow that direction. 5, 0. 2, negative 1. And then I'm going to do my best to connect my dots. I draw these things better sideways. Something like that. Why do I think it is drawing better sideways? I don't know. Yeah, maybe it's just the angle. I'm not sure. There it is. So one more time before we turn the page. Are there any questions about the math that you've seen done? Yes, Hunter.
So if there's nothing in front of the square root bar, right?
No number in front of the square root bar?
Number in front of the square root bar, or no number in front of x, won't the graph always look the same?
Okay, so if there's a positive number on the front, it points up like it should.
Well, yeah, but it always looks the same, like.
Well, it'll be stretched if there's a number in front. And if there's a negative number on the front, it'll be upside down, so it'll point down. Now, as far as x is concerned, as long as x has a positive number on the front, it'll point towards the right. Of course, I could put a number in front of x, like a 2 or a 3, which would be a horizontal dilation.
Well, it just changes, like, the way that they're pointing,
Right? But again, you're just looking for positive or negative.
Yeah.
Negative changes orientation because negative signs are reflections. Okay? Any others on how I know what to plug in, why I'm choosing 0, 1, 4, plotting my dots? Nothing? Big old geniuses. That's good. Great. Then we'll turn the page and we'll go to the quote-unquote difficult one. It's not difficult. It's just that, well, we're going to have to work a tiny bit harder to figure out what makes the inside equal 0. Before we do anything, though, we will determine the directions that this thing points. See a minus sign in the front, so it points down. And the number in front of x is positive, so it points right. Down and to the right. Have I graphed in green yet? I have not. Down and to the right. It'll look like that. We set the inside equal to 0, 1, and 4. And we figure out what we have to get. So we'll have to work a little bit harder this time. Whatever. I haven't graphed in green, so I'm writing in green. Subtract 4 from both sides. And divide by 2. Okay. Subtract 4 from the both sides. And divide by 2. Ew, a decimal. It's okay. It's a pretty one. It's a 1/2. It's easy to plot a 1/2. Subtract a 4 from both sides and divide by 2. We know our x values. Because 3 divided by 2 is 1.5. We don't have to work for the first y. We know that whatever makes the inside equal 0, comma the number to the far right, is always going to be our end point. So it actually happened at -2, -1. And you might be a little concerned about the fact that you have to plug in a -1.5, but remember, when we do plug in -1.5, all it's going to do is make the inside equal 1. I mean, that's where we got this x value from. So guaranteed, when we plug this back in, it's going to make the inside equal 1. Let's prove it. 2 times -1.5 is -3. -3 plus 4 is 1. The square root of that 1 is 1. Oh, but it's negative. -1 minus 1 is -2. And then x equals 0. 2 times 0 is 0. 0 plus 4 is 4. Hey, look, it made the inside equal 4. How about that? Square root of 4 is 2, but it's negative. -2 minus 1, -3. Here's your 3 coordinates. Yep, -2, -1, -1.5, -2, 0, -3. I'll put a little EP right here because that's my end point. That way I don't accidentally put the arrow in the wrong place. Not to mention, you know, we've got this picture that tells us which way it goes. And like I said, I always draw these things better sideways for some strange reason. So like that. And there it is. So the question becomes, how do you feel about graphing square root functions? Yes, Hunter?
So the negative in front of the square root.
The negative in front of the square root forced it to point downwards instead of upwards.
But this negative in the square. Oh wait, no, there won't be. Yeah,
Well, there could be. Look, this one had a negative in the square root,
well, yeah, but
and so did this one.
when you do the graph,
Well, it's not that I got rid of it, it's that the x's I chose ensured that I was always going to take the square root of a positive number.
I was looking at it, I was like, what if it's an
Ooh, we're not graphing imaginary numbers in the real number system.
Yeah, so
It requires a completely different graph.
it has to be positive on the inside of it.
When you're plugging in your x, the inside must be positive or 0, yes. That's why the graph doesn't exist to the left of -2. If you go to the left of -2, all your points are imaginary. Okay. Yes, ma'am.
Would the domain be -2 to infinity?
This one's domain is -2 to infinity, yes.
And range is -1 to infinity.
-1,
Oh wait, not
but it points down.
so negative.
So negative infinity, but if you're going to say negative infinity, you actually have to say it first. So this one's range is from -infinity up to -1. The reason why we say it first is because our intervals are always supposed to go from small to big, and there is nothing quote unquote smaller than -infinity. It's the most negative thing you can imagine. And you know what? I'm actually kind of very glad that you asked that question because it's pertinent to the next example. Look at that. It's like she knew. Now check this out. The function from above and its inverse, which I'm just telling you, this is the inverse. I found it by hand. This function and its inverse are right here. I want to know what the domain of this is. Now, notice the title of this says Inverses and Restricted Domains Revisited, because we've already learned this. It was on the mid-Chapter 6 test, and that question did not do well. In fact, it did incredibly poorly. That is why it's in the notes again. So we're going to talk about it again, and I'm hoping that now that you know how to graph square root graphs, this kind of question is much easier. Because yes, it is on the chapter test, and it will be on the test review, but it is not in the homework because it's old material. The homework is just the graphing because this is not new. I don't need you to practice it anymore unless you are not good at it. And if that's the case, feel free to go on to Schoology and grab the 2 reviews from the mid-chapter test and tackle that question again. So here we go. It says, what is the domain of f inverse of x? And you have the ability to answer a question like that without ever knowing any of the functions. Because you could walk up to me and say, hey, if you know f and f inverse, what's the domain of f inverse? And I could answer with the exact same statement every time. Is there anybody that remembers, and it has nothing to do with the graphs that we're doing, what the domain of an inverse will always be?
All real numbers.
It won't be all real numbers.
0 and up.
Nope.
0 and down.
Nope.
Down and 0.
Nope. That makes no sense. So nobody knows? Nobody remembers? How about this? How about a different question? How do you find inverse functions?
Reverse it.
What does inverse mean? What does that mean? How do you find it by hand? If I gave you an equation, you switch x and y. Now, if you switch x and y, what two things about the functions have switched?
The domain and range.
The domain and range. So then what is the domain of f inverse always? The range of?
The regular.
F of x.
Is your pencil hot?
Yeah, the two equations, because this question had nothing to do with the equations. No matter what the equations are, the domain of the inverse is always the range of the original. The domain of the original is always the range of the inverse. Because x and y have switched places, domain and range have switched places. Now, we look back at these. And in order to find the domain of this quadratic, so that these two things are one-to-one, because the way it sits, they are not one-to-one. That's a two-sided graph. That's a one-sided graph. In order to make them one-to-one, you have to eliminate half of the quadratic. But which half, you ask? Well, I'm glad you asked. The range of f of x will be the domain of this. And then just a moment ago, Piper and I had a conversation about the range of that graph. This is the way it's shaped. You see, we didn't have to graph it to know that. And earlier, Hunter asked me, what good would knowing the shape do you if you could just find the coordinates? Well, what if this was the question and it had nothing to do with graphing? You would go, well, it points down and to the right. A little bit of mental gymnastics, and you can see that -2 makes the inside equal 0. So you know your endpoint. And then, Piper, what was the domain of this? The domain. What's the domain of this? -2 to infinity. That domain is this thing's range. Piper, what was the range of f of x? -infinity to -1. Good. So if you would like to know which side of the quadratic that you're allowed to keep, you're allowed to keep this side. Happens to be the left side. Because this thing's axis of symmetry is at x equals -1. Half of it's on the left of that axis of symmetry, the other half's on the right of that axis of symmetry. Just so happens we have the left side. Because you can tell me the domain and range just by looking at this. In general, so this is going to be a generalized rule that is always true for quadratics and square roots. The domain of the quadratic is, I'm going to use the word always, and I'll put it in capitals, the range of the square root. We'll put a box around it because it's a rule. An unbreakable rule about inverses. The domain of your quadratic will always be the range of your inverse radical. Always. So hopefully on the chapter test, when you see a question like that again, I'll have much higher success rate, especially now that you know how to graph these things and what they would look like without even graphing them. I hope. It's what?
What was the
Like 50% success rate. I don't know what you got. I just know that the success rate was F. That's what I know. And if only half my students are getting it, well, need a little bit more review and practice. That's why it's in the notes again, but not in the homework again. Huh? Okay. Now, let us graph some cube roots. Booyah. This is the parent cube root. You will notice it has an arrow on the left and an arrow to the right. Its domain is all real numbers. But why is its domain all real numbers? Because you could take the cube root of anything. That's why. Cube root of a negative is negative. Cube root of 0 is 0. Cube root of a positive is positive. And since it can go forever for left and right, and your cube roots never get, they just get bigger and bigger and bigger and bigger and bigger, and or more negative, more negative, more negative, more negative, its range is also all real numbers.
So it's true, like, always?
It's always, all cube roots, they exist everywhere on the graph. Now, this thing has a center. It has point symmetry, or rotational symmetry around its center. The academic vocabulary for that point, which happens to be right here at 0, 0, is the inflection point. That is what that is called. You'll learn why it's called an inflection point if you go to AP Pre-Calc next year. For now, just know that's what it's called. And if you call it the center, I'll know exactly what you're talking about, and I'll just say, okay, yeah, that's fine. I don't mind. Okay? Good news! The inflection point, the center, is found by asking yourself, what makes the inside equal 0, comma, the number to the far right. Isn't that cool? It's done exactly the same way. Yay! But you know what? I don't know what the cube root of 2 is, or 3, or 4, or 5. What I'm getting at is, just like with the square roots, we need the things underneath the cube root to be very special. What kind of numbers do we want to see under our cube root?
Nothing.
Cubes! You want perfect cubes under there, so you could take the third root by hand. And, remember, they exist for positive and negative x's. So you don't only do the positives. What you do is you find the center, and then find me 2 points to the left and 2 points to the right. Find the center, 2 points to the left, 2 points to the right. That's difficult. Okay, anyway, but you get it, okay? So guess what those 5 cubes are that we're looking for? 0's the one that is in the middle.
1.
So 0, 1, negative 1, 8, negative 8. Remember, they're symmetric. They're symmetric around their inflection point, around their center. These are the 5 smallest perfect cubes. And that's why we're going to go for those 5. And you might be thinking, oh my gosh, I got to find 5 points? Man! Well, you don't actually have to plug in all 5. In fact, in just a moment, you're going to see that you really only need to find like 3 points. Just go with me here, okay? Now you'll notice the space here is larger. That's because we have to write inside equals 5 different numbers. So inside equals negative 8. Inside equals negative 1. Inside equals, I wrote x equals. Inside equals 0. Inside equals 1. And inside equals 8. Dang it, I did it again. There. I'm going to do you a solid. And what I'm going to do is I'm going to tell you, what have I not graphed in? Have I graphed in blue yet? Yeah, I started in blue. I'll go back to blue. Here's what you're going to do.
You make the inside equal -1.
You're going to start here, and you're going to go this way with finding your numbers. Trust me on that, okay? Just trust me on that. The cube root of -1 is -1, Hunter, so we don't have a problem with negatives. It's cube roots, okay? All right. If you subtract a 4 from both sides, what you're going to get here is x equals -4. If you subtract a 4 from both sides, what you're going to get is x equals -3. And if you subtract a 4 from both sides, you get x equals 4. Now, I'm going to set up my t-chart. I know that I haven't found the other ones, so I'm going to make it tall, but I'm going to leave some space. This one's going to go in the middle. 4, -3. Wait, forgot a negative sign. And then +4. Check this out. What do I have to do to get from a -4 to a -3? Add 1. And what do I have to do to get from a -3 to get to a +4? Add 7. Great. Let's find this number real quick. Subtract 4 from both sides. And what you're going to get is x equals -5. What would you need to do to get from here to here? Subtract 1. It's a symmetric movement. +1, -1. Subtract 4 from both sides, you get x equals -12. Hold on. And to get from -3 to 4 was +7. So this is the opposite direction, -7. The graphs are symmetric. So once you find these 3 numbers, these 2 numbers are free. You just go the opposite that these did, movement-wise. That's more than one question. Hold on. Maya? It will not always be 1 and 7, no. But whatever the movement is symmetric movement. It's just the other direction. Okay? Now, let's plug this number in. Oh, wait a minute. It's going to give us -1. We already know that. Great. Now, let's plug in -3. Let's plug in -3 and see what happens. -3 plus 4 is 1. The cube root of 1 is 1. Times -2 is -2. -1 is -3. This is a coincidence that they match. Put no stock into this at all. It's coincidence. However, let's just track the movement. -2 that way. So guess what is going to happen here? Add 2. It's symmetric movement. Let's plug in 4 now and see what happens. 4 plus 4 is 8. The cube root of 8 is 2. 2 times -2 is -4. -1 is -5. That's interesting. Subtracted 2 again. So add 2 again. Someone's got to have the question. It's got to be itching someone's brain right now. Yes, Hunter?
No, that's not my question, but if there is a number in front of x...
If there's a number in front of x, it's going to change these movements because that's a horizontal stretch or shrink.
It won't be 1 or 7 anymore?
That's why Maya asked if it's always 1 and 7. It wouldn't be 1 and 7 anymore, no. Yes? Riley? Because okay, what's the cube root of 0? What's the cube root of 1? 1. What's the cube root of 8? What's the cube root of 27? 3. You see how I've asked the questions, what's the cube root of? And the answers that you gave me were 0, 1, 2, 3. Okay. The reason why is because the y's are cube roots. The x's are you plugging in x's that will make a cube. Okay? So you have to plug them in. Let's plot these dots. -12, 3. -5, 1. -4, -1. -3, -3. And 4, -5. These are kind of tough to draw. I do them better from my inflection point down. That's just the easiest way for me to draw them. And there it is. And there's not much more to that one. Now, unfortunately, with only 3 minutes left in class, I don't have a chance to finish the notes today. But that doesn't mean you don't have the full capabilities to finish the homework. However, please pay attention. Examples like this one, you're still going to start it the same way. You're still going to ask yourself, what makes the inside equal -8, -1, 0, 1, and 8. And then just follow the patterns that these things have, and you'll be able to graph. The 2 in front of the x, all it's going to do is change your x distances from 1s and 7s. That's all that'll do. Okay? So, give the whole homework a crack. That'll do it.